some subjects which I hope will help you to understand the past lectures. And then if you are staying for the next week, will help you to understand some of the lectures. So let's see. So yesterday we were talking about the relative invariance. So the relative invariance, so we were talking about m bar gamma and y e, where gamma is the topological type of this. So an element here is really a map or morphism to YL and map to Y. Right, and yesterday we were talking about this YL is a singular variety, but it's a very mild singularity. And there are all of these. And we talk about pre-deformability condition. Which means that basically your curve mapped to this. So the curve has to map to that, and because this is a constant, beta dot E is a part of data. This is sort of in your mu is part of data. This is topological number, right? So intersection of a curve with a divisor is a topological intersection. So this is constant D, and therefore you have to map D here somehow. And so the curve here, every time you have this singular part, and your curve has to split in two directions, and they have, this is usually also called kissing condition. That means the two parties who kiss each other has to have exactly the same contact order. Right? So that's the pre-deformability condition we're talking about. And once that's true, then you can smooth it out and then become a smooth thing. So become one. Whereas original two, they said this is a part of necessary condition that when you smooth this out, and the curve can also be smoothed out. Okay, so now to tell you a moduli functor, I just have to tell you one more thing, which is when two maps or two morphisms are considered isomorphic. So I say this, two of them are considered isomorphic. So they're isomorphic if there is an automorphism here, which I'll say. So sorry. So this is if there. This is what we called last time phi, and maybe I'll call it psi. Now I'm allowing automorphism of YL. And what is the automorphism of YL? This is a C star action on every of these P1 bundle. So L of them. X on the P1 bundle. Excuse me, sorry. So this is, remember, I attached this Y by P1 bundles, right? And every P1 bundle has a fiber-wise C star action. and that is the C star. But so every one of them has 1, so it's C star to the L. And remember, this is very different from the usual Gromov Witten theory, that the target, in the usual Gromov Witten theory, first, the target does not change. And here is target does change. That's why the target also has some kind of moduli. Target also has some kind of moduli, which David denote by this script T. And secondly, I'm allowing target to have automorphism, but not on the Y part, not on this Y, originally your Y part, but on the P1 bundle part. And once you have this, then this sort of then you have to generalize what I said in the point case to family case, which is not particularly difficult. And I wrote some kind of hint how to do this in the family case, but it's actually very straightforward. So now you can show that this form a proper Lee-Mumford stack. And yesterday I was asked why you would need this to, for example, you would need this to be predeformability condition, and why you need this to bubble off. And well, I mean, the predeformability condition and bubble off, and also this quotient. So first of all, why do you need this allow automorphism? What if I don't allow automorphism? If you don't allow automorphism, this moduli stack won't be separated. That means it's not Hausdorff. That means you have two kind of sequence. Well, you have one sequence. We can have many different limits, and by quotient this out, then you make all the limits become the same. Okay. Does it make sense? And why is that? Because you can approach. So you can approach your this is how you construct this. It's sort of more like blowing up this way, and then if you approach it with different speed, even though it's sort of the same approach, it will give you different limit in the blowing up. So that's why. So anyway, so you have to think a little bit about this. We are almost out of time. This is the last one, so I do want to get through a few things. And so this is a relative thing, and you heard David talking about like what one can do with relative invariance. So first thing is that it has extra structures. For example, this m bar gamma y. So E. It has two evaluationmorphisms. I mean, so there is a EVY to Y, maybe to the n, right? So there is this evaluationmorphism to Y, just as usual. In like this Donaldson-Thomas theory, there's no evaluationmorphism there, but we do have evaluationmorphism just because when I map to here, if there is a mark point, here, and so if there is a mark point inside, I can take a mark point mapped here and map down here. So it definitely evaluates to Y. But also I have evaluationmorphism to E, to a row. So I used row yesterday. Is this. So this is so this partition into row part. So I have row points on E, right? So this is all these points, row point, and I can evaluate those points which will go to E. Okay, so you have extra this kind of evaluationmorphism, and these evaluationmorphism will as well as like this is the same target, so you also have this map into this script T, this module of target. So this is somehow this in. No. Let's yes. No. Oh, yeah. So the point here, so the modular point here will be so whenever you have an L, which this happens. Oh, yeah. So sorry. So yeah. Okay. Whenever the L, this happens, and I forgot to talk about. There is also stability condition. So to define this, I do. So these are what we would call pre-stable relative maps, and then to form this moduli, I also require that this kind of, for every L, I can define this pre-stable thing, and it will be a modular point, and as long as it satisfies pre-deformability condition, etc. So, and I want the stability condition to be that, again, the automorphism of a map has to be finite. So then, sorry, so the stability, I forgot to say this, stability condition, a finite automorphism again. So L is something you can choose by yourself, or for given L, if you have this, then it becomes one of your member. But the problem is because I'm allowing this automorphism, so here as well. So if you do, if L just expand indefinitely, it's not going to be stable. So you have to think a little bit about that. It's very similar to if you bubble off too much in your domain, you won't be stable. This for the same reason. Does that make sense? You thought about this, right? So in the stable curve case, if you bubble too much, then it won't be stable. Even for maps, if you bubble too much, you won't be stable because you only have finite degree. Given beta, I mean, the only way it can be stable is either it's already the irreducible component is stable, or it has to map non-trivially to your target. But the degree is finite, and therefore you cannot grow indefinitely. That's sort of boundedness statement. And the same here. If you allow your L to grow indefinitely, it's not going to be stable. You will be pretty stable, but won't be stable. So that's why I need this condition. And once you have this, then you form this moduli. It has all these, basically all the properties you could have. For absolute case, you could have that for relative case. And so, and also, so this is, then you get moduli stat. Proper type. And also by the same, well, it's much more, a little bit more involved statement, which will not say too much, is that you can also find, can define perfect abstraction theory, and therefore it really sort of define the virtual class. And therefore, you can define the relative invariance. And so once you get into this step, then you can ask what these relative invariants good for. And this, in David's lecture, I was talking about that. I was sort of ahead myself. That these relative invariants has that, extra structure help him to solve one of the problems. And then, so also, it is important because, how does this come out? Well, you can think about this relative invariance in two ways. One, what is geometric meaning of the relative invariance? It means that I'm going to study some kind of refined Gromov Witten invariance so that I can specify. So this is a given my G, N, and beta, I can specify, well, I have this topological intersection with a divisor. If I specify that my contact order with the divisor has to be like have row 1 up to row mu 1 up to mu rho, then that sort of is a subclass of these maps, right? Generically, generically it will be 1, 1, 1, 1. But if I specify like here, there will have to be one point which has count over 2, the other point has count over 3, etc., etc. Then you select out a subclass of these maps, and then I do compactation of that. That is so it's sort of a refined Gromov Witten variance. Although this interpretation is not heuristically. So these are sort of refined Gromov Witten invariance. Counting number of maps with specified contact type with E. But this is really heuristic. The interpretation is often wrong. And you can hear more from Andrew's talk next week. But really, also there's so this is sort of one motivation. Another motivation is that I can use this to state the degeneration formula. So the degeneration formula says that this is what it's been used a lot in attribute geometry, right? So if I have a family and then it degenerates, then I want to be able to study my variety by its degeneration. So for example, if I can relate, like in the last lecture you heard about like this quintic in P4. Of course I can degenerate this quintic to, for example, to union of phi plane in P4, or not really plane, but phi P3 intersecting. And so if I can get information from that degeneration to my quintic, then that would be great. So that's something we use a lot in attribute geometry. So you would want to be able to study degeneration formula. And there's some kind of effort to do it in a more general degeneration, but what I'm going to talk about is a very simple degeneration. It's double point degeneration. So if you have a double point degeneration, then you will be, so for example, if you have what is, do I use any notation here? No, yeah, I use different notation. I have to change this. So if I have this, this is a double point degeneration. A double point degeneration means that pi is flat, and so I call coordinate on T1, T, Wt are all smooth for T not equal to 0, and Wt at W0 I can write this as A union B, where A, B are smooth, and they intersect transversally, and in the divisor D. So that's called double point degeneration. So basically what you see here is something like smooth, smooth, and then at the center the central fiber becomes a double point degeneration. Maybe like this. And this is your A, B, and then your D. WT. So that's the diagram. And for this kind of that you want to be able to say that a Gromov Witten theory of WT is Gromov Witten theory of, this is your W0, right? This is W0. That's what I'm going to say. Well, after all, Gromov Witten theory is deformation invariant. It's a deformation invariant. So this should be true. But there's no definition of Gromov Witten invariance for this kind of singular normal crossing variety. Okay? And so what can I do? Well, if I want this to be true, I have to define this in a way so that it is true. Does that make sense? And how can I define this? Well, the only thing I have is I have A and B and intersect at D. So as a matter of fact, this degeneration formula will tell you that, so this is, what is this, right? So the question is what this. Can I define this first, and can I define it in a way that it's actually equal? And if you can, then it's a very good thing, because you can do a double point degeneration to something really simple. For example, this is the definition given by Mark Levin and Rahul Pandaripande. They proved that all smooth variety can going through double point degeneration can be changed to just projective spaces. So you can basically, if you know how to deal with this, you don't have to deal in principle projective spaces. But that is a little bit too far. I will not say too much. So okay, so how to define this? So to define this, you will have to use the relative Gromov Witten variance of A respect to D and relative Gromov Witten variance of B respect to D, and combine them in a certain way. To combine these two, then I can define it by this combination. Okay? That's the only way we are able to define it so far. Well, old definition, the target has to be smooth projective variety. Now it's not smooth.
Yeah, but which part exactly does it want? We have this modular space table map to verify. Virtual class doesn't support
That's it. Why do I? Okay, so.
Why can't we try to mimic the old construction?
Well, think about it. Why can we? Okay, maybe an exercise will be, why can't we do that? If I just, if I just take a map of curves into this space, this is an algebraic variety, right? So I can still talk about space of maps to this W0. What goes wrong? Yeah, a good exercise. That's also why I need pre-deformability condition, etc., etc. So they're all sort of linked to each other. So if you think about that, then you understand why you can. I mean, maybe you can. It just doesn't. To rephrase what Jun Li said, it's just obviously you can. But well, if something is not obvious, it can only be better, right? So if you work out, then it's a theorem. It's no longer just a trivial observation. Anyway, so that is something you have to do, and I will not state the degeneration formula in detail because we just don't have enough time. But it's written in the notes, so you can, if you're interested, you can read that. So basically, you have to define this. The only way to define this is going to be combining these two. Combine these two in a way that it will make sense. And so we have some certain like understanding of orbifold cohomology. So I'm going to skip that. Is that okay? Yeah. So I know it's okay with you. So, but I don't know. Anyway, so Alessandro certainly spoke a little bit about orbifold chain-run cohomology, and then maybe Gromov Witten invariance for orbifolds. So I want to say too much. I don't want to say too much, but I think if you read the notes should be very readable, because especially because I just copy from my collaborators' writing. So it's basically it's copy. It's a lot of them are copied from my paper, but it's written by my collaborators. So it should be very readable. Anyway, so the last topic I want to talk about is the Crepant transformation. Or K equivalence. In Gromov Witten theory. So if you think about Gromov Witten theory, say, hey, we defined quantum cohomology, right? So we defined quantum cohomology on Wednesday. You say, oh, quantum cohomology is a ring structure. So you can ask, if I have a continuous map or a morphism, maybe I'll say y to x. Given a morphism, wait, did I use f? No. Good. Because f is the map, right? So even though it's important to abuse the notations, to have any math done according to Alessio-Corti, I can't abuse them too much. So the f usually is your map from a curve to the space. So if I'm given any morphism of y to x, which I call phi here, and now you can ask whether the phi pull back quantum cohomology. After all, it does pull back cohomology. So does phi tilde go from here to here as ring homomorphism? Well, this is a ring, and this is a ring, and it's called quantum cohomology ring, and this quantum cohomology ring. Since it works for classical cohomology ring, you might wonder where you can pull it back. The answer is just flatly no. And it actually is very simple, very easy to see. Well, first of all, how do you define quantum cohomology? Well, we define it in a way that it's defined by Gromov Witten variance, right? So you first look at Gromov Witten variance, say, hey, now, if I want to do this, I will have to be able to do, like, let's just say 3 points. You can do any n points, y, beta. This certainly mapped to m bar 0, 3, x. By functoriality of our maps, this certainly works, right? It obviously works for every map, and then by functoriality, for families it also works. So the moduli stack will map to that moduli stack, no problem. So if you have evaluation-morphism to you have 3 mark points, you can map. So that certainly can pull back to here, no problem. There's no problem of pulling this back all the way to y. So you can ask whether this is true. So did I give that a name? maybe not really. Well, I didn't really give this a name. So let me give this a name called maybe m bar of phi, just to avoid more notations. So if you add, and if EVX, and then of course you have this EV to y cube, and this is v cube, but I'm just going to denote it by phi again. So I can pull it back here or pull it back to here. Either will be okay. So I'm just going to say maybe I'll first pull back here, and my any alpha class, and then pull it back by y. So is that going to be the same as so that would be our sort of natural reduced this kind of question. Does that make sense? Okay, but then if you look at this won't be the same. Why? Well, the answer no really come from here, because if you count this guy and that has absolutely the same cohomology degree. I pull back does not change cohomology degree. So the degree is the same. However, you compute so I said degree and the dimension of virtual class has to be the same, right? But if you compute the virtual dimension on the y side, and this is certainly not necessarily the same as virtual dimension in the x side. Oh. Fine. As you know, what is the main possibility of this? Well, this is a morphism, right? So morphism, what are the main type of morphisms? Well, there is this, for example, you can have embedding, right? You can have smooth morphism, or you can have birational morphism, borrow up. There's basically three main types morphism. Let's just and for all these, if it's embedding, then the dimension will not be the same. And so you might think, well, let's take a dimension the same. Then that it also excludes smooth morphism. But if dimension is the same, then it's broken up. But broken up, you know the broken up formula, right? So ky will be the same as pullback of kx plus codimension minus 1 of your broken up, say, broken up smooth center, then of your exceptional locus. So obviously it changed. This is not pullback, and so this won't be the same in general. Does that make sense? So it does change the minus k dot beta. So the virtual dimension won't be the same. And so in that way, that this functoriality will certainly not work. So this does not pull back. That means, well, it is sort of quantum cohomology, but it does not pull back. And if you think a little bit about this, this is very natural. Look, those which had those objects which are very functorial contain very little information. Otherwise, how could it be functorial? It moved from here to there, and without any obstruction. That means carries almost no information. Cohomology, for example. I mean, I'm not saying cohomology contains, but it contains only like functorial informations, anything not functorial has to be dropped from these. So that's why cohomology is very easy to compute because it's a very simple thing. Quantum cohomology, very difficult to compute because it's very complicated. It cannot be functorial. If it's functorial, then quantum cohomology has to be very simple, and it's not. So we have to change this. We have to find a way to get rid of this, or to change the situation. So from this discussion, you see that the way to make this pull back or something possible like this possible is to make sure the dimension the same, right? Dimension has to be the same, and this canonical line bundle also has to be the same. So dimension is the same, that means blow up, basically. But for any blow up, the canonical bundle has to change because you know the canonical bundle formula, canonical divisor formula, right? So it cannot also be a blow up. So what can that be? Well, that is something we're going to talk about. So it cannot be a blow up, but dimension will be the same. And then the canonical class has to stay the same. So what can that be? Well, if you blow up, then blow down, then that would be. So here is a definition of K-equivalence. The definition of K-equivalence saying that if I have phi here and phi prime here, so both are birational dominant morphism such that you can say this Y is a common resolution of X and S prime, even though X and S prime already smooth, then I say they are K-equivalent if the pullback of the canonical divisors are the same. Well, so that's, and they are of course birational. Right? So this X and X, these two are birational. And they have common resolution. And then I call them K-equivalent if they have the same, basically the same canonical class in a natural way. I mean, of course, they are different varieties. You cannot say they have the same divisor, right? Different variety, how do you say they have same divisor? Well, that means because they are birational, I find common resolution, they pull back to a common resolution, they become the same. That's the only way you can compare the canonical class. So this could be a blow up, this could be a blow up, but I blow up, then blow down. So in this way, they become the same. Questions? And so this is if you want to say X and X prime are K-equivalent, or you can say we'll say that X and S prime is K-equivalent, or if you want to emphasize that you're going from one to the other, this X to X prime is a Crepant transformation. So that solved the problem. That make the functoriality, so that sort of we found the defect of functoriality could come from here. These has to be a necessary condition in a certain way. Does that make sense? If you want to have like a functorial property of Gromov Witten invariance, these have to be a necessary condition. And also, just to, so X and X prime can also be orbifolds or smooth Riemann stacks. It doesn't have to be manifolds, because in that case you can also define Gromov Witten invariance or quantum comarginate of orbifolds. You can also ask the exactly same question. And the special case of this is maybe a special case, a very special case here is that when you have some kind of a x bar which has quotient singularity and which has this x, maybe this x as like an orbifold, or I mean to be, this is a smooth stack. And then you have also, in this case, you might also have a resolution, so called Crepant resolution. If in the case that x bar is singular, then it could have Crepant resolution. As I said, if it's smooth, then smooth, and if it's morphism, then the canonical class cannot be the same. Cannot be the same as pullback. I already told you the formula there, right? But if this is singular, they could be the same. And in some singular case, for example, if these two are the same, the canonical class, if the canonical kx is the same as kx bar pullback, they call them Crepant resolution. And really, this is another resolution which I resolve by smooth orbifold. So in this case, that's a special case which has been talked about a lot, called Crepant resolution conjecture. But really, Crepant resolution conjecture is it's a small corner of a very much bigger category. You call Crepant transformation. That's why I don't like call Crepant resolution, because it's too narrow a class. And in fact, if you read the notes, which I don't have time to explain too much, it's also misleading. In some phenomena which happen in Crepant resolution, it could be very special. I mean, also, if you look into the special phenomena which might be misleading. That's why I would advocate to look into Crepant transformation first. So I explained that this sort of is a necessary condition for Gromov Witten theory to be functorial. So you can ask whether that's sufficient condition to make it so. Okay? And it turns out that so the conjecture is that so this is also sufficient condition. Well, in a very subtle way, for xs prime are really manifolds, and for orbifolds, there's some kind of something called Harlots property. Some sort of Harlots property will influence how functorial this thing can be. In Harlots is the Harlots you learn in the first chapter of Griffith-Harris. I just mean that. And of course, for any smooth projective manifold, you have Harlots property on their Hodge structure. But you can ask well, that is not true for all the orbifolds. Right? So if you want to have something which orbifolds resemble manifold, as we want, right? Gromov Witten invariance of orbifold, you want to resemble Gromov Witten invariance of manifold. This is something you probably want to preserve. That's what. And of course, there's a few proposals how to get rid of Harlots property, then your functorial property will be very weak. Well, it will be weaker. I wouldn't say very weak. It will have to be a lot weaker. And that's something let's see, we can talk about. Okay, so this is the case. So let me explain what could be going on in this case, and then let's just for simplicity, let's start with manifold case. And what's the simplest example of this kind of K-equivalence or Crepant transformation? It's a flap. So I will first give this example of doing the flap. For example, if I have here is Z, which is a projective space, and it's inside, this is my Z, inside X, and this X has a normal bundle, so this is normal bundle of this Z inside X. So I have normal bundle of Z inside X to be to make this Z locally look like BL. So I require my Z inside X locally look like it's going to be O minus 1. Locally. That means I have so this X would have to be 2R plus 1 dimensional, right? So because I have a smooth subvariety, the Z is smooth subvariety, which has no bundle of rank R plus 1. So it's 2R plus 1 dimensional. And I require it to be locally the same as O minus 1 to R plus 1. You remember the canonical class of projective space, or any canonical class of projective space is O R plus 1. So I just sort of cancel out all the. So locally becomes trivial. The canonical class becomes trivial here. Questions? And in this case, bearing on some kind of projectivity assumption, I can shrink this projective space to a point. This Z can be a point. This Z become a point. Z mapped to a point. Or I can blow this up and when I blow up this Z becomes oh no, this is not just locally. This is forget about that. That's globally. So okay, so when I blow this up, this Z becomes your exceptional divisor becomes this. Let me try to draw it so it's sort of parallel to that. This becomes your exceptional divisor, and exceptional divisor will look like PR cross PR. If it's trivial, so this is globally, not locally. Does that make sense? This is easy. And so now if I have two, so this is my sort of a Z project PR, and this is another PR direction. And I brought it up with this PR. Now I can brought down along my Z direction, original direction. So this becomes the Z prime inside X prime. And Z prime can map to a point. And this is the simplest example you can find in this R-dimensional space, such that you can prove that these two have the same canonical class. So, I mean, how do we prove this is the same canonical class? Well, it's very easy to prove, right? I already told you how I brought it up. And so you can pull back, you know, the canonical class is the same as this pullback plus R times exceptional divisor. This also plus R exceptional divisor, but the same exceptional divisor, and therefore they cancel each other. So this is a K equivalence. Right? By canonical divisor blowing up formula. And so that would be your test ground for what I said. Gromov Witten theory has to be the same. So that's the first case. We can think about this and see if they're the same. Okay, so what is in fact, in this case, one can show that. So look, these are all sort of a. Oh no, I should have drawn this like this direction. It's better. That direction. That, okay. Anyway, so just schematically. So here's the theorem. Well, which I sort of will be pre-theorem, which of a lecture I will give next week. The joint work with this Professor Lin and Wan from National Taiwan University. Is that in this case, the Gromov Witten theory of X is actually the same as Gromov Witten theory of X prime for all genus. But why do I put this weaker line instead of an equal? Because this actually requires called analytic continuation. What do I mean by this? Yeah, so if you stay in to the next week, you will hear something about analytic continuation for this, how this has to work. But in the simplest case, I will say that the following has to be true. That what do I mean by analytic continuation? So remember how I define Gromov Witten invariance. I define as a formal function of nomical variables. Are defined as formal function of nomical variables Q beta. So it's just a formal function. But I can choose, if I choose a direction which is exactly the curve inside Z. Remember, Z is a projective space. So Z is a projective space. So up to equivalence, there is exactly one line inside this. There's one line class inside projective space. Okay, and this line class associates a nomical variable. So there is this, you have summation, and so this has QDL. will be your numerical variable in that direction. Does that make sense? And so you can ask what this is about is that first thing I have to say, what I have to say here is that this Gromov Witten theory. So the first thing you have to explain is Gromov Witten theory is an analytic function in this QL. In this numerical variable. For other numerical variable, I have no control whatsoever. It's by definition, it's formal. They are all formal variables. But for this line class, I have better control. I have to show that it is an analytic function. In fact, it's a rational function. So in fact, it's a rational function in Q. In this particular Q, you have many Qs. You have Morricone, which many generators, etc. So you have many variables, but for other variables, I have absolutely no control because they are very general. But for this specific line class, I know exactly what the local structure is because it's inside projective space. So it's a sort of local PR. But this local PR in the normal direction has O-1 to R+1. So there is a lot easier to deal with. So this is the analytic function. And then what do I mean by analytic continuation? I have to so this and so the Gromov Witten theory is so usual Gromov Witten theory is sort of a series expansion. So Taylor series expansion at Q equal to 0, right? Q line equal to 0 because that's we define formal series. If I don't say it, that means based on 0, right? So that's what. So now, if you analytically continue that, because the analytic function, so the QL now it's a function on P1. No longer just a formal disk, but it's actually a function on P1. Now, I analytically continue that to infinity, and I re-expand. The generating function to QL to P1 and expand it at QL equal to infinity. And then you get Gromov Witten invariance at x prime. So you start with Gromov Witten invariance of x. You start with, so maybe I should say Gromov Witten invariance as a generating function for x. And you do this and you do that. And so one is the expansion at 0, one expansion at infinity. You get this. And so this is a complicated procedure, and it's difficult to prove because usually what we like to prove is two Gromov Witten invariants are the same. So for example, if you have two localization, if every fixed locus they are the same, then they are the same. But here you cannot do it. You have to form a generating function which becomes an analytic function. And you have you really have to be able to sum it formal series up and show its convergence and show its analytic function and analytically continue that to another point and re-expand that at the point.
Do you choose this L in the Z prime case also?
Yeah, so yes. So this QL, so in other words, yeah, so something I will say in the next, but I will now say, so in other words, I'm making QL correspond to Q minus L prime. L prime is the line class inside the Z prime. That's the reason I want to write this Z prime Z is because they are all projective spaces, right? So this, but So you correspond to negative of that. So obviously this statement doesn't make sense, because if you think of Gromov Witten theory are power series in Qs, and it never going to go negative. That means you're using a negative curve class, which by effectivity axiom, the Gromov invariants are 0. But it holds only in this sense. Oh, by the way, I should say that the R equal to 1 case was proved by Yuan-Pin and Jun Li first, and we generalized to higher dimensions. They all, yeah. And so, not only that, so I want to make this statement even more precise, is the following. I want to make this not just like, for example, if I give you x and x prime, then what you can do here is to compute Gromov invariance on x, right? And do analytic continuation to the other side, you get Gromov Witten theory of x prime. But that is sort of a set of data correspond to a set of data. But can you tell me which one corresponds to which one? Right? This is two different things, right? So one is saying, well, I know if I do this procedure, I will take this set of data and correspond to that set of data. But can you pinpoint, like, an element here will go to which element? Does that make sense? That's a more refined statement. So, in fact, what is more true is that there exists an isomorphism of this, which send the line class I was talking about to negative line class here. And I can make an even more precise statement. Here is the following. So if I take alpha 1, alpha n, take any g n, but now not really beta, I have to sum over all degrees. So beta, I will say this beta 0, but I have to sum over d, where you have this q dl plus beta 0. Okay, if I do this, and this will be, in this same sense I was talking about, it will be the same as if I sum over d prime of f of alpha 1, f of alpha n, but g n beta 0 prime, which I will have to do d prime, but beta 0 prime. So the beta 0 prime I can erase. If the curve class is not inside, they will be mapped to and the other effective curve class to effective curves. That means if your curve does not involve this effective, so exceptional locus, it will become another effective curve. So how do I do this? Well, easy way to do it would be to pull it back to y, then push down. So on the birational, because these two are birational, x and x prime are birational equivalent. So if a curve is outside, you pull it up, then push down, it's still another effective curve, right? So you're good. So that our effective curve will go to effective curve. So I'm just going to erase that part. That effective curve I fix. Now I start to sum this effective curve inside the exceptional locus. Because inside exceptional locus, they cannot be the same, because effective curve map to ineffective curve. And the reason that the only way they can be the same is through this analytic continuation process, which I just explained. So there is this, so So all the Gromov Witten, so that means Gromov Witten invariants on X side. You don't have to know all the Gromov Witten invariants on X side instead of to do all the Gromov Witten invariants on X prime side. I only have to know Gromov Witten invariants for fixed alpha insertion for fixed G and fixed effective curve outside. But I have some overall effective curve inside Z. Okay, if I do that, then I'll get exactly that. Does that make sense? So you still have to compute infinite many Gromov Witten invariants to get infinite many Gromov Witten invariants, but that is, you know, a big refinement from what you have. I mean, in fact, this is the minimum you have to do, because, as I said, the L will map to negative L prime, so that part cannot be literally true. And to sum this, well, I mean, the summation requires something in G and 0. I think Mr. Tsai has a very good result about how this G and 0 computation, how you can sum over this as an analytic function. So by some kind of virtual localization technique. But that's anyway, so that we don't need that, but I would say this is following true. So once you have this, you can try to think, well, what if X and X prime? So this is the first example I said. The first example you can verify. Now you can start to think, hey, what if X or X prime or both are orbifolds? Okay? What if one of them or both of them are orbifolds? What can I do about it? So can this still hold? And the answer, as I said earlier, it cannot obviously hold, because there's some kind of Harlots condition which sort of this actually, so the Harlots condition, so it was observed by really Alessio Corti and Tom Coates and Hiroshi Ritani and Xianghua Chen. I think, well, I mean, at least 3 of them, Alessio's here, and then at least 2 of them will be here next week. So they observed that you do need some kind of Harlots condition. It's reasonable. Once it's been observed, it seems to be natural. You have to require something. But if you so in case X or X prime orbifold, so then you don't expect or can expect this to hold in general. So again, you need some kind of Harlots condition. But what kind of Harlots condition we have to require? So if you think about this Crepant resolution, it's a little misleading, because anyway, so once you think about this, you say, hey, these two are birational orbifold, but they're birational anyway. So you say, okay, so let's look at this. For example, if it's Crepant resolution case where one side is orbifold, one side is manifold, or it could be like both sides are orbifold. If you think about this, you say, well, what's the minimal requirement I have to put in for this kind of strong statement to hold? Well, of course, you can say I want X and X prime both are satisfy Harlots condition. But that is a very severe constraint on the orbifolds. There are not many orbifolds. Actually, most orbifolds do not satisfy a Harlots condition. So you severely sort of handicap yourself about it. And that's when you only think about Crepant resolution. You have this kind of idea, because look, one side is X is certainly satisfy Harlots condition, so X prime has to satisfy Harlots condition. So if you think about only Crepant resolution, then you naturally impose X prime to be also satisfy Harlots condition. But if you don't restrict yourself to that category, then you think x and x prime are birational, then what's the minimal condition I can require? I have to require that they have to be Harlots only on the exceptional locus or neighborhood of exceptional locus. Does that make sense? Because outside they're the same anyway, right? Whatever non-Harlots they have, they share. So they're the same. Only when they're exceptional locus and its neighborhood, when they can be different, and it has sum over the Gromov Witten invariance, only then you have to require Harlots condition. That's what I call Harlots K equivalence. So this is I think reasonably the minimal requirement you have to put on your Crepant transformation so that this kind of strong statement can hold. Does that make sense? Means it's only you only require Harlots condition on a neighborhood of your exceptional locus. In the Crepant resolution case, you have to require that to hold in general, basically, because I mean, if they're birational on the place they're birational, they satisfy Harlots. Since x satisfy, the curly x have to satisfy, and in the sectional locus you have to satisfy, and therefore it's satisfied in general. But here, if your x and s prime both orbifolds, then it could happen that they're outside they're nasty, but only in the exceptional locus they satisfy Harlots condition, and the nasty part they share, so they sort of the same. Only in the exceptional locus where they could be different, then you require them to satisfy Harlots condition. So that's one thing we can. So I hope this will help you with next week if you're staying for the next week. And so what if you want to prove, as I said, so what if you don't even want to have this to satisfy this Harlots K condition? If you don't want even this to satisfy HLK condition, what could it be? Well, then there's no hope that this kind of strong statement I just stated can hold at all. So, and you have to find a weaker functoriality statement. And this weaker statement is sort of developed by many people and eventually written up in a survey paper by Tom Coates and Yuan-Pin, and you can find out in the reference. So that has to use sort of a Giventhal formalism, etc. So that's why I include as a lecture 3 in introduction to Giventhal formalism. But unfortunately, as you and me realize, there is no, we just don't have enough time to talk about everything which has to be covered in Gromov Witten theory. So that I will not say too much. Okay, so maybe just to wrap it up, I will tell you a little bit about how one can prove this in the flap case, the basic case. So in fact, this is just that kind of standard or simple flap I explained earlier. Well, I have my local geometry is explicit. Local geometry is very explicit, but global geometry is arbitrary, right? If you are like a differential geometry, you would think I just take my local geometry and glue to something, and I glue to another thing. So it's kind of surgery. I just change locally this. So, of course, the hope would be say, well, if I can make my Gromov Witten theory into two parts. One is only survive in the neighborhood. One is only survive outside. That would be perfect because the outside they're all the same. They have exactly the same geometry. And neighborhood they are different, but they are explicit, so I can calculate them as much as I want or I can. Does that make sense? So I want to. The first observation is I want to say the Gromov Witten theory of X is sort of a somehow Gromov Witten theory of neighborhood of Z inside X, and sort of combined with Gromov Witten theory of the outside X minus Z. If I can do that, that would be great, because then you write this down. If I can do that, then that will be the same as Z prime in X prime, and then Gromov Witten theory of X prime minus Z prime. But these two are the same, so this part is the same, and I only have to do this part. Okay, that's sort of a very naive expectation, and of course it cannot be true, right? So first of all, Gromov Witten invariance has to define a projective variety, and this is open. And also, the local geometry does interfere with global geometry. Gromov Witten. So, if you think about very hard about Gromov invariance, the hardest part for me is say how does it different from like study of rational curve in a variety. Studying rational curve in variety usually study a real rational curve inside variety. Every curve counts for itself. But Gromov Witten invariance is studied for curve classes. I specify a class, and the class can be represented by all sorts of different curves, right? And so a lot of techniques in, say, Morris theory cannot work here just exactly because they're studying like an exact curve, and we're studying curve classes. And the class can, for example, if you have a class which apparently like outside here, I can deform that because it's same class, right? So same homology class. I deform it, and eventually it becomes, so maybe I'll use a different color. So I have a class here, and then eventually deformed to be something like this, for example. And then part of that lie inside, but they are the same class. So even if I start with something which is completely outside, I have to that include information from this exceptional locus because it's the same curve class. So that is something which is completely wrong. On the surface, this statement just cannot hold. Does that make sense? But that's sort of the beauty of this degeneration formula. What does the degeneration formula tell us? That if I do degeneration, I have to suffer from this new refined, like this stacky kind of a target, moving target thing, and relative Gromov Witten invariance. But what I do have is if I do deformation to normal cone, this can be deformed into blow up of Z X union deformation to normal cone. So this is a deformation to so maybe so everybody knows deformation to normal cone, right? Who doesn't? Nobody. Okay, great. So I know the trick is to ask questions the right way. If you ask the other way, so nobody knows. Like if you ask this way, everybody knows. So you just have to ask questions correctly. So anyway, so this deformation tells me that if you do deformation to normal cone, that'll give me this. And on x prime, I can do the same thing, which give me that. But if you look at the diagram, which I skillfully did not erase, was these two are actually the same. They are all called y there, right? Aha. So once I have degeneration formula, then I can say this part is actually the same. So I only have to deal with projective bundle case. And this projective bundle is really the projective completion of a normal bundle, which is a neighborhood of that. That's exactly what I want. Well, not exactly, but the best I can hope for. Does that make sense? So now I have this I have to deal with. The only thing I have to suffer is I have to learn relative Gromov Witten variance. But you have to learn that anyway, right? So all right, so that is the first step. So you reduce that to local case. So the degeneration formula relative Gromov Witten invariance on projective completion of neighborhood. So I mean, this is probably not really. I mean, of neighborhood of exceptional loci. So so I only have to deal with. Now you have to compute. But look, what do we have to do now? We have to compute the Gromov Witten invariance for this part. So what is this? The projected neighborhood. If I may, I will say that I write this like that. It looks very intimidating, but really, what is Z? Z is just projective space. Your projective space, and these are just O minus 1. Right? So it's a projective bundle over projective space. So this is a toric case. It's a very simple kind of toric variety, toric manifold. So as you learn from Alessio's course that, well, at least you heard that they are computable in principle, right? So now you have to be very disciplined and compute them and use some tricks. Then you can compare. So these you can compute. Can compute in principle in genus 0, right? So he wrote down some kind of formula for J function, etc. And I explained the notes, which I did not have time to explain in the lectures, that in genus 0, once you're able to compute J function for toric variety, then in principle you can determine all descendant invariants from this kind of reconstruction. So one way to do it, in fact, that's how we did it, was to compute J function first. then use reconstruction in genus 0, of course. Genus 0, J function only defined for genus 0. Reconstruction, which in my paper with Pandaripande. There's going from small j function, of course. Big j function is not computable. Small j function, you can, by reconstruction, you get all descendant. And so you can, well, but actually, here is a trick. So descendant is not correct. You can get all descendant, but you don't want it. You only want this to be primary invariance. Or ancestors. These are okay, but this is not. These two, for whatever reason, well, actually, there is a good reason why descendant invariants are not. So when I said Gromov Witten theory, I did not say, remember, I only wrote alpha 1, alpha n. I did not say tau k1. The primary invariance, that strong form of conjecture or theorem I stated hold for primary invariance. Did I erase that already? Oh, no, I did not. So this holds for primary invariance. It also holds for ancestors, but does not hold for descendant. And okay, so I have like 1 minute. So I would say, well, for those who knows, or all of you, that means all of you, because you all know your ancestors and descendants, right? So if you haven't learned it, it's halfly your mistake, halfly also mine. So anyway, so descendant is defined on the moduli of maps. So when you sum over degree, for every degree, it should change, right? When I change degree, it's a moving thing. You just keep changing. Ancestor, what is good about ancestor? When degree change, the same ancestor pull back. So it's more universal. If I compare both sides, it's something which I can map to. So if I have m, they all map to the same m0n. So it's universal, shared by both. That's why if you prove it for the primary invariance, you will more or less hold for also for ancestors. I just add more like universal classes. And in a sense, what other classes you pull back? You pull back from x, right? So you pull back from x, n. But xn really, it's basically the same as this, right? Because as I just said, these two are the same. So you pull back the same classes anyway. So the classes which will hold are the universal classes, means it doesn't change with your beta. And class doesn't hold, which so descendant. And so this is actually one of the difficult things of proving this theorem is to, because every time you do any geometric operation like localization, descendant just show up, as I showed you the other day, right? We use that for good purpose. We start with some kind of 1, and we get j function, which is a descendant invariance. But descendant just show up, but you don't want descendant. It's an invalid guess. So what can you do? Well, if you're as polite as I am, you cannot kick it out. So you have to do something about it. Like, try to shove the guest out of your door and without any nasty words. And once you're able to do that, then you prove the theorem. Okay, that's the conclusion. All right, thank you. For genus 0, yeah. So for higher genus, again, I did not explain because then it requires the second, well, actually the first appendix, which is the quantization. I do have to go through this quantization business, whatever that means, to go from genus 0 to higher genus. And in general, you cannot quantize the Gromov Witten theory of X, but you only can quantize Gromov Witten theory for this local projective toric variety. And that's why that's another sort of incentive for you to do this degeneration formula. Yes.
When you define the K equivalence,
yes.
you need all maps to be birational.
Yeah.
But,
yes.
Why can't we allow the degrees of the two morphisms of the correspondence to be different or greater or equal than 1?
Well, if you have a finite morphism, then definitely you change the canonical class, right? So
I mean, for example, a dark cover, it doesn't change anything.
You asked me why I want this to why don't I sort of include a tau cover of a variety to this discussion? Well, in principle, I can, but so, and everything you do will be up to a degree D, and then certainly there is a morphism, and there might be some kind of authority, although I haven't really thought about that. To be more precise, so a precise statement is I haven't really thought hard about that. So I don't know whether that's going to work. Obviously, you're going to miss a lot of Gromov Witten invariance to be sure, because every time you have like say y has a tau, it's like finite a tau to x. Okay, so all the class from y will have to be like d times class or primitive class in x for sure. Right? So you're missing a lot of Gromov Witten invariance from x. Whether that's the only thing you miss, or you can recover in some way, I don't know. But definitely the Gromov Witten theory cannot be absolutely the same. Do you see what I mean? So you have the beta here. They basically have the same, but then you're missing a lot of things. And so whether you can recover that, I don't know. I haven't really thought very hard about it. But definitely, again, it's not obviously true. But if it's not obviously true, but it's true, then all the better.